But you never post them, right?
All right. That's because I need to edit them first to remove all the mistakes and insert in, laugh tracks and stuff like that. So it makes it seem like my jokes are funny. Have you ever looked at a mirror?
Yeah. Oh, yeah.
Because sometimes it looks like you've never looked at a mirror. When you look inside a mirror, there appears to be space, and that space is called virtual space. Virtual space. Inside, like living inside a mirror, which is very weird and bizarre. But if we base our assumption that light travels in a straight line, which we kind of do, we've even drawn it, we're solving those refraction problems, we drew optics and light as just a ray. We simplified it to be just one ray of light. And when light hits a mirror, this is all about reflection. What are the three types of mirrors? There are plane mirrors, which is just flat. There are concave mirrors, which, to be a perfect optical concave mirror, it would actually be a parabola. However, it's pretty hard to manufacture perfectly parabolic mirrors. So instead, we typically say that they are part of a sphere. Okay? But the math that we use is as if they are parabolic. What's special about a parabola? It has a focal point. Question?
Yeah, is that a spoon?
Is that a spoon? No, this is just a drawing.
No, I mean like the kind of.
Yeah, exactly. Like if you look on the inside part of a spoon, the other type of mirror, you probably already know, is convex, which is just looking at kind of the outside part. It's just bent in a slightly different way. And again, we're treating these as if they're part of a circle. Now up here I have concave and convex mirrors. And if you look at the way that they are bent, and these are pretty small, they have certain properties, and they're also very useful. When you think about what is the point of a mirror is supposed to show you a reflection, and probably an authentic reflection. Although in my house I buy those like skinny mirrors that kind of look like the kind they have in department stores, where you look at them and they're bent in just slightly a certain way, where you look a little bit skinnier than you are.
Really?
I have body image problems. Anyway, if you look at a mirror, they can also be used to do different things. I don't know if you guys have ever seen a shaving mirror or a makeup mirror, where if you look closely enough, you appear magnified. Yeah. So you can zoom in. I don't know why you'd want to zoom in.
I know.
Have you guys ever read Gulliver's Travels?
No. I heard that.
Seen the movie? It's written by Jonathan Swift. You guys have read something by Jonathan Swift, right?
Oh, yeah.
A Modest Proposal. I love A Modest Proposal. It's, it's just a modest proposal to solve famine and overpopulation simultaneously. But listen, Jonathan Swift, I just think this is interesting. He wrote about what would the world look like if you were really, really tiny and you got to look up close at a human being. And it's kind of a misanthropic novel. Do you know that word? Misanthropic. He talks about what the world would look like if you were really small and you got up close and personal and actually looked at someone's face, and just how ugly it would be that zoomed in. But anyway, so mirrors can help us magnify light so that we can see magnified images. They're also useful in other ways. There is, on the corner of our parking lot, there is a convex mirror. In the corner of a convenience store, there might be a convex mirror in the corner. On the side view mirror of certain cars, in fact, most cars, there is something written on the side of cars. You know what's written on the side of cars? Objects in mirror are closer than they appear.
Doesn't it say maybe?
Yeah, it might say maybe closer than they appear. Why would your car do that? hey, look inside this mirror. It may not show you an accurate depiction of reality. Good luck driving. Try not to hit anybody. Why does it have that message there for you? Why do you think objects in the mirror are closer than they appear? What would make something seem closer than it actually is? Well, no, actually, I guess it's saying the opposite. What would make something seem farther away than it really is? Objects are actually closer. You look at it, things look farther away. Why is it actually closer than it appears? What would do that? What would make an object seem farther away than it really is? If you made it look...
Smaller, like then.
Well, that's why it's going to look smaller. But if an object normally looked a lot smaller than it is, then it would seem, you'd think it's far away, right? You look in your mirror and you're like, oh, that car behind me is tiny, that means it's farther away. We look at the sizes of objects and help determine how far away they are from us, right? Depth of perception. So what your car mirror is doing is it's making things look smaller. Why would it do that? If things get smaller, you can see more. Your car mirror is intentionally sacrificing something for you. It's giving you a skewed, deceptive view of reality so that you can see more, right? Everything's smaller, but if everything's smaller, you can fit more into your window of vision, if that makes sense, right? By bending the mirror, things look smaller, and therefore you might think they're farther away. Hey, that little tiny car, no, it's right next to you. Don't change lanes right now. It's important the way that we use mirrors. So now let's talk about some of the properties of mirrors, okay? What is the focal length of a mirror? Even a plane mirror, technically you can talk about its focal length. The idea is if you took a plane, or actually if you took a concave mirror from a sphere and started to straighten it out, you would eventually get a plane mirror. What's the focal length of a mirror? The focal length is the distance from the vertex of a mirror to the point where incoming parallel light will converge. Okay. Now you might look at this and be like, wait, light's not going to converge anywhere if I shine it on a plane mirror. It will never converge. It will never come back together. You could probably look at a concave mirror and say, oh, if I shine light coming in this way, all parallel, yeah, it's going to bounce and it's all going to reflect inward, right? So it will indeed converge here, but on a plane mirror, it's not going to converge at all. If light hits this mirror, it's just going to bounce off, following the law of reflection. Well, we're going to get to this in a minute, but it turns out that the focal length of a plane mirror is infinity. And it turns out that the focal length, what about of a convex mirror? Light comes in this way. Light comes in this way. What happens to that light? It bounces away just because of the shape of it. Light doesn't converge at all. But it appears as if it does if you trace this line back. So what we will learn soon on the other side is that a convex mirror has a negative focal length. Okay? What the heck is a vertex? The vertex of a mirror, if you draw a straight line right through a mirror, wherever you want to define it to be, kind of like the origin, I guess, the vertex is right where, so let's write this down as well. The vertex is where the optic axis, say straight line, passes through the mirror. The vertex and also the optic axis are just our reference points. You know, we're like, how far is everything from the vertex? We're just picking that to be like our origin, so we can describe points and their distance from them. How is the radius of curvature of a mirror related to its focal length?
basically with this equation. The focal length is equal to the radius divided by 2. So the radius of the mirror is just how curvy it is, right? So there's the radius. And the focal length would be exactly half that. Okay? That's what it says. The focal length, I'll write it in words. Focal length is half the radius. Okay? And this is not precise. This is our very first assumption that we're kind of making. It turns out it's a really pretty good assumption as long as your mirror is not gigantic. If the radius is really big, you're going to be off just slightly. Okay? But we're making the sacrifice because spheres are easier to deal with than parabolas. A parabola would be exact. Okay? What is the object distance? What is the image distance? The object distance, we're going to abbreviate this. We're either going to use DO or SO, depending on the book that you use. D indicates distance, S indicates distance, and the O means object. So this is basically how far is the object from the mirror. The object is the source of light. It might be the flame from a candle. It might be the sun. Or it could just be any object. It could be this binder clip. It could be this car. Because objects, as you know, opaque objects will reflect light. Okay? So if I stick this object in front of a mirror, the distance between the object and the mirror, that's called the object distance. Got it? Piece of cake? Okay. No problem. What is the image distance? We abbreviate that with DI or SI. That is the distance from the vertex to the apparent location of the image. Where does it appear to be? Okay, now I have to try to draw a picture for you. See what I can do. Let's go here. Bam. There's our plane mirror. And let's say that you were standing right here. And here we go, boom. There's you're wearing one shoe. And you're wearing one glove. Okay, in honor of Michael Jackson. And you are looking at the man in the mirror. Okay? You will see your image. Now, we've all looked in a mirror. We've all seen this. Okay? Have you ever seen, in the end of those old movies, there's always a cool chase scene, one guy's got a gun, and the guy always ends up in a carnival and then goes into the house of mirrors, you know what I'm saying? And there's all these reflections, and then the bad guy fires at the good guy, and you think he's gonna kill him, but then he just shoots a mirror because he thinks it's a reflection. No?
Yeah.
All right.
That's one of those horror movies. Pretty cool. Everywhere, and then
Huh? Oh yeah, the glove's on the wrong hand. Look at that. Switcheroo. There we go. Sorry. Okay. And now I have to draw this other weird thing in real space. Now, okay. Here's the question. That's a fist. And that's a heart. The question is, which side is real and which side is not real? One side, and you have to pick, is called real space. And the other side is called virtual space. And I want you to think about why it appears this way. And really, it's all basic. This is just the law of reflection. This is really easy because this mirror's flat. Think about this. You look down, there's your eye, and you see your shoe. You look down in real space, and you see your shoe in virtual space. And the reason is because light reflects off of your shoe, hits the mirror here, and bounces back up the eyeball. Okay? Light from your hand heart thing bounces off the mirror and reflects back. But if you trace that back, that line back into virtual space, boom, it appears to come from there. We trace these lines back. That's why we see ourselves in virtual space. Now, just to make the math a little bit easier, if you are standing 3 feet from the mirror, how far into the mirror, into virtual space, are you standing? Another 3 feet. Okay? Another 3 feet. In other words, for a plane mirror, D, actually I guess I should use S. I'll use S from now on, okay? I think our textbook uses D, but the AP equation sheet uses S, so I'm going to use S. SO equals SI for a plane mirror. Okay? You do have that left-right inversion issue, but that's why we see what we see. We assume that light is traveling in a straight line. That's why it looks like it's coming from inside the mirror. Okay. And things, of course, are going to get much more complicated when we talk about curved mirrors. How far an object, how are object and image distance related to focal length? There's an equation that's called the lens maker's formula, and it works not just for a lens, but also for mirror. It could be the mirror maker's formula. 1 over SO plus 1 over SI equals 1 over F. Okay? Add the reciprocals to get the reciprocal. Okay, and that comes from some geometry. I'm not going to derive it for you yet. What's the magnification of a mirror? The magnification of a mirror is just a ratio that relates the height of the O. Okay, it's the height of the image to the height of the object. And I will draw for you over here HI, HO. That's off to where we go. These are equal to each other. HI equals HO for a plane mirror. So what's its magnification? 1. Okay, when you start bending the mirror, it gets weird. But not only does M equal HI over SO, it turns out that it also equals negative SI over SO. If you end up, can you end up with a negative magnification? Yes, that doesn't mean your object gets smaller. You could have a magnification of 3/4, which would mean your image is 3/4 the object. That would be a diminished image, shrunken. A negative magnification means the image is inverted. Okay? I can look out at you guys right now looking in this concave mirror from a distance, and I can see you upside down. Hi, Stephanie, you're upside down. You see me?
Yeah.
Why are you upside down? You can invert images inside mirrors. How does magnification relate to... I just told you. I jumped the gun on that. That's fine. So what is magnification? It is just a ratio of image height to object height. Pretty obvious. Exactly what you thought it would be. What is the difference between a real and a virtual image? Well, here's the actual authentic difference. In a real image, light actually converges to form the image. A virtual image real light diverges but appears to converge. In, I want to say inside the mirror, but it still sounds weird to me. Inside the mirror. Okay. There's another tip just to help you remember that makes life a lot easier. A real image is always inverted. Inverted, I mean upside down. It's always upside down. A real image is always upside down. A virtual image is always right side up. Okay? We haven't practiced solving any problems. What I want to do though is I want to talk about how to solve problems in optics. And there's two ways you can do it. One is you can geometrically verify, because here's the idea. You will often basically want to know, one, what is the focal length of this mirror? Or two, if I put this object in front of a mirror, what's it going to look like? How tall will it be? Where will the image be located? Those are the questions you want to answer. And to do that, you can either use these two equations, I guess 3 equations, that all show up on the AP equation list, or you can just use geometry and draw it. You either use algebra, or you draw it using geometry with a ruler. Okay, so I'm going to show you the rules to follow when you're doing it with geometry. Okay, the first thing is, let's come up with an image. Okay, before I do this, I guess I should have labeled a few things for you. If I were to trace this thing around, like to make the full circle, where's the center of the circle? Maybe right there. So I would put a C to indicate the center of the circle. And if I look at this, I'm like just kind of guessing here. So you can do the same, just guess. There's the focal length. Okay, the focal length is halfway between the vertex. It's the vertex. And the center of curvature. On this side out here, I'm going to say, well, let's trace this around. There's the center C. There's the vertex B. Okay. Now, what kind of object do you want to have? Well, I'm not very good at drawing, so we're just going to start. I'm going to try to make one kind of easy. I'm going to make a candle. Okay? And that's my object. So I'm going to draw from there all the way there. That's my SO. Now, this light, this flame is giving off light in all directions. So there are an infinity of rays emerging from this candle flame. But what I'm just going to do is I'm going to draw 2 of the most important, most relevant one, and I'm going to give them funny names because that's how I roll. First one is called Ray Charles, which is awesome in both the fact that it's named after Ray Charles and also the fact that it's ironic since he was blind and we're naming a ray of light after him. It's just awesome. Okay. A few more things about this. This is also, we'll just label it type HR. Okay. So how do you draw Ray Charles? The other thing is Ray Charles is very critical of your drawing, so for obvious reasons. Ray Charles comes in parallel to axis and passes through focus. I draw these little arrows also to indicate direction, which is actually really important. So there's that ray, and it comes out. Bam. I realize that this is a lot easier if you have a ruler, and you probably don't have a ruler, so do your best. That's Ray Charles. Okay. So, what do we draw next? Ray Lewis. They'll hit you pretty hard if you screw this one up. How do you draw Ray Lewis? Ray Lewis comes in through the focus and out parallel. It's kind of the opposite. Come in. When I say out parallel, I mean out parallel to the optic axis, of course. Okay. Are there other rays? Heck yeah, there's other rays. They're just not as awesome like Ray Romano. Not quite as funny. There are other rays that we can draw, but these two are the best. There's another pretty easy one. Maybe I'll draw the third one. So you get to this point, and then you ask yourself a question. The question you ask yourself is, do the outgoing, I don't know why I call it outgoing, reflected rays intersect? If yes, then you have a real image. If no, trace them back into virtual space. So what do we have? Do these guys intersect each other? Where do they intersect? They intersect right there. Now look, I know they also intersected at the focal point, but that's not both incoming rays. Or that was one incoming ray and one reflected ray. We want the intersection point of both reflected rays. They're outgoing rays. So that happens right here. So what you would see here is a little tiny candle. That little tiny candle would be located right there. So SI, that's the SI, and it'll have a little tiny height, HI. I'm sorry it's so horribly written in there. But here's the conclusion that we draw from this particular case. Okay? If SO is bigger than F, if SO is bigger than F, think about what that means. If you place your object at a distance that's greater than the focal length, you are going to have a diminished, inverted, real image. Okay? You're going to have, you are going to create a one, diminished. Diminished. Two, inverted. Three, real image. Okay. Have you guys ever taken a spoon or any mirror like this? If you start, any concave mirror, if you start far away, okay, and look in the mirror, okay, you see tiny little, like for you guys, I see, this reflection that's tiny, okay, hey Ricardo, inverted. If I start kind of getting closer and closer, first what happens is, you can even see yourself, if you're far enough away, you can see yourself upside down, inverted, there I am. Okay. In this case, I happen to be kind of large. Bring it in closer, suddenly it gets fuzzy. It gets fuzzy and fuzzy and fuzzy and fuzzy and larger, and then suddenly it starts to get clearer and magnified. Okay, so something changes when you bring an object closer to a concave mirror. So the position of this really makes a difference. If you bring it too close, suddenly you get a magnified upright image. If it's far away, you get a diminished inverted image. Okay? let's talk about what happens with our convex. I guess we should write next to this concave and convex. Okay. Again, we'll do the same thing. Let's place our candle out here. It's got some HO. It's located distance SO. We're going to draw our Ray Charles again. The rules are the same, but now it's a little weird because the focus is on the other side. So I bring in, the ray looks like that. And now I want to draw it in through the focus, but here's the thing. Mirrors, the light bounces off. So I've lined it up. You see what I'm doing here? I'm lining up this point right here with the focus. I'm just going to draw a dashed line down here. And on this side, I'm going to draw a solid line bouncing out. Why have I drawn a dashed line? Because this is inside the mirror. How do I draw a Ray Lewis? Well, you'd aim for the focal point. I'm going to aim for the focal point. I'm going to draw it down like that, and then I'm going to stop. Should I continue to trace the dashed line in? Heck no. That light is coming in. We only trace back line that's reflected off. What happens to Ray Lewis? Ray Lewis comes in and it bounces off like that. Parallel. That is the ray we trace back. And we ask ourselves, do the outgoing reflected rays intersect? No. Look at them. They diverge. Two rays diverge in an empty wood. See where they intersect right there? They intersect in virtual space. We will get, that's our little object. Okay, a little tiny candle, that's HI, that's SI, okay? An object in front of a convex mirror will always, this is what's great about a convex mirror, it's easier. Concave has all these different scenarios. Convex does not. If you have a convex mirror, an object in front of a convex mirror will always appear. 1, diminished. 2, upright. 3, virtual. Okay? Jamie.
When you draw your little Ray Lewis line, how do you decide like the angle on how steep to make it? Or do you
This angle?
Yeah.
It was going to go through the focus.
Okay.
Okay, that's why. It was going straight toward the focus, and then boom. Okay, it bounced off parallel, just like what it says. Comes in through the focus and out parallel. Okay, assuming that it can. Now, there's a lot of other stuff in this packet. You should take a look tonight. We'll go over this grid next time. There's a couple more lines drawn for you. This last page, this is what we will do in class next time. Okay, we'll practice tracing ray diagrams. Your homework for tonight is more about refraction again, just more refraction practice. There's also 2 book problems that I have written here. It's page 707 and then 45 and 46 written on here. So it's basically just these. It's, in fact, there's no ray tracing. There's no mirror problems for homework yet. Okay? 45, 46. It's also written on this worksheet.